All right, in this video, we're going to go over combinations of functions and composite functions. Now, there's four ways you can combine functions. You can add them together, you can subtract them, you can multiply them, and you can divide them. All right. So if you added them, it would look like f of x plus g of x. If you subtracted them, it would look like f of x minus g of x. If you multiplied them, it would be f of x g of x. And if you divided them, it would be f of x over g of x. All right. So let's look at some examples here. F of x equals 2x minus 1, and g of x equals x squared plus x minus 2. All right, if we wanted to add them, f of x plus g of x would simply be 2x minus 1 plus x squared plus x minus 2. All right, so we really don't need the parentheses, so we can go ahead and combine stuff. So we have x squared plus 3x minus 3. That is what f of x plus g of x would look like. We're simply adding the two functions together. That's all we did. Just added the two functions together, combine like terms. All right, let's look at subtract. So f of x minus g of x would be 2x minus 1 minus parenthesis. Make sure you write this parenthesis. Would look like that. Now, it's important to make sure on the subtraction you write the parenthesis. I get in the habit of always putting the g of x or whatever function your second function is here. I get in the habit of always putting it in parentheses. That way, when you do the subtraction, you don't forget that you have to distribute that negative through all three of the terms. So that's what you get after you distribute, and then of course you can get rid of the parentheses. So now combine like terms. So it's x squared, 2x minus x is plus x, negative 1 plus 2 is plus 1. So that is what f of x minus g of x looks like. All right, so you can see they're totally different. All right, now if we multiply, we're going to have f of x g of x. So it's going to be 2x minus 1 times x squared plus x minus 2. You simply FOIL, basically. So we have 2x cubed plus 2x squared minus 4x minus x squared minus x, and then plus 2. Now again, you just go through and combine your like terms. We have 2x cubed, then we have 2x squared minus x squared, which is just plus x squared. Negative 4x minus x is minus 5x, and then we just have the single plus 2. All right, so that is f of x g of x. All right, hopefully I didn't make a mistake. I did that kind of quickly, but I think it's right. Yep, just checked it with the book. All right, now let's look at divide. I'm going to leave this up here so we have those two functions. Now let's look at division. All right, if we have f of x over g of x, we just have 2x minus 1 over x squared plus x minus 2. All right, now, even if you factored the bottom, we can't simplify this any further than this. This would be x plus 2 and x minus 1. You should know how to factor. All right, so we can't simplify this. Now, I know you know what domain of a function is. It's the x values that you can plug in to make the function make sense. Now, if we look back at these, we don't really need to restrict our domain for any of these because there's no fractions or square roots there, or there. Because really the only time you need to restrict your domain is when you have a square root or a fraction. Well, when we divided it, we now have a fraction. Remember, when you have a fraction, the denominator cannot equal 0. All right? So this here, we cannot divide by 0. So we do now need to restrict this domain. Okay? How we do that is, we said, since we factored this, we're going to set each one of these equal to 0. If this wasn't factorable, you just go ahead and set it equal to 0 and then solve it out. Like if it was just, say, 2x plus 1 equals 0, 2x plus 1, you just set that equal to 0 and solve it. So we know that x plus 2 equals 0, so x equals negative 2, and then x minus 1 equals 0, so x equals 1. So now, our numerator, we don't have a square root there, so we don't have any restrictions there. Because if we had restrictions there as well, we'd have to take into account those restrictions also. But since we only have a restriction in the bottom, our domain here, all right, our domain is going to go from negative infinity to negative 2, all right, because x can't equal negative 2. Union would go from negative 2 to 1, union 1 to infinity. Now, the reason we have to break it up like that and not just say that it is negative infinity to positive infinity is because we can't include negative 2 or positive 1. And this is the way to break it up, if you want to write it in interval notation, to show that negative 2 and positive 1 are not included. You could also say something like x equals all real numbers except negative 2 and 1. Right? You could really write it either way. I'd kind of prefer you write it in interval notation though. All right. So that's it for combining functions. Now let's look at composite functions. All right, now let's look at composite functions. What composite functions are is you're taking one function and evaluating it at another. Here's what I mean by that. You have f of x equals 3x minus 4, and g of x equals x squared minus 2x plus 6. All right. Now, there's a new little symbol you need to learn. For composite functions, it's f, a circle, a little circle, and then g of x. All right? Now, whatever function's first is going to be your outside function. Whatever function is second is going to be your inside function, so to speak. Okay, so this is your outside function, and this is your inside function. What does that mean? Well, it means that we're going to take f and evaluate it at g. So any place we see an x in f of x, we're going to write in g of x. So we're going to have 3 g of x minus 4. What does that look like when we plug this in? Well, it's going to be 3 parentheses x squared minus 2x plus 6 minus 4. See, all we did was take g of x and plug it in where we had an x. That's all we did. Now this would need to get distributed through, so 3x squared minus 6x plus 18 minus 4. So it would be 3x squared minus 6x plus 14. That would be the composition of f and g. So f composition g of x would simply equal 3x squared minus 6x plus 14. All right. Now, what about if we wrote it this way? What would it look like? Well, now we're taking f and we're putting it inside of g. Okay? Because remember, this is the outside, this is the inside, so we're putting this inside of g. So this would be basically f of x squared minus 2 times f of x plus 6. So we would have 3x minus 4 quantity squared minus 2, 3x minus 4 plus 6. And we would just simplify this down. So this would be 9x squared minus, 24x plus 16 minus 6x plus 8 plus 6. So 9x squared minus 30x, and then 16 plus 6 is 22, plus 8 is 30. All right, so 9x squared minus 30x plus 30. All right, that's your F composition G and your G composition F. And if you notice, they are not the same. That does not equal that. All right, when you flip them around, they do not equal the same thing. They are completely different functions. All right. Now let's look at one more quick example of a composite function, and I'm going to show you how now there's a different process to restrict your domain on a composite function. So say f of x is 2 over x minus 1, and g of x equals 3 over x. All right, and we want to find f composition g of x. So this would simply be 2 over g of x minus 1, because every place you find an x, we're going to put g of x. So it should be 2 over 3 over x minus 1, which simplifies out to, because you multiply top and bottom by x to get rid of the fraction here. So times x over x to get rid of the fraction. So we're going to have 2x over 3 minus x. All right, that is our F composition G of x. All right, now restricting the domain, because as it looks, the domain is only, it can't be 3. Well, that's not true. We have to take into consideration that both of these domains up here, namely just the g of x. So x is not in the domain of g. It must not be in the domain of f of g. Okay? So if x is not in the domain of g, it must not be in the domain of f of g. All right? Meaning here, our domain here is x cannot be 0. So therefore, 0 must be excluded from our domain of f of g. Even though it would work, since it doesn't work for g of x, it cannot be in our domain for f of g of x. That's what this is. All right, so any restrictions you have for g of x still hold true for f of g of x. All right? So that's your first condition. Your second condition is any x for which g of x is not in the domain of f must not be in the domain of f of g. All right, so what does that mean? All right, well, if we look back up here, all right, we have to exclude places where g of x equals 1, because then that would not be in the domain. Okay, so we have to exclude places to where g of x equals 1, because then here it makes it divide by 0. So we have to take 3 over x, set it equal to 1, and solve for x. All right, so of course we'd multiply both sides by x, that'd cancel that, so 3 equals x. All right, so therefore the domain of f of g of x, all right, we can't include 0 and we can't include 3, because, again, our two conditions, if x is the domain of g, it must not be in the domain of f of g. Well, 0, x equals 0, is not in the domain of g, so it can't be in our new domain. And then we also can't include 3, because any x for which g of x is not in the domain of f must not be in the domain of g of x. So here, all right, the domain, because you can also write this as f of g of x. So that's what they mean in the domain of f. So therefore, g cannot equal 1, okay? Because then it would be 0. So at x equals 3, g equals 1. So our domain cannot include 0, and it cannot include 3. So our domain would look like this. Negative infinity to 0, not including 0. Union 0 to 3. Union 3 to infinity. All right, so that would be our domain of f of g of x. All right, even though it looked, like I was saying, even though it looks like 0 would work, since the 0 does not work in the g of x, we can't have it in the domain of f of g of x either. And also the 3, since g of x minus 1, since 1 would make that equal 0, we have to set this equal to 1 and figure out what x value that is. So in this case, it's 3. So therefore, 3 cannot be included in our domain of f of g either. All right? All right, last quick topic is decomposing functions. Meaning, we have an h of x, which say equals the cubed root of x squared plus 1. What we need to do is we need to find an f of x and a g of x so that f of g of x equals h of x. So now we're thinking backwards here. All right? What does it look like could be our g of x? Remember, the g of x is a function we put inside of f. All right? So what could be our g? What could be our f? Well, if you notice, if we made f of x the cubed root of x, then the g of x would simply be x squared plus 1. All right? Does that make sense? I couldn't hear what you said, so hopefully it does. All right. So, or if we had, say, an h of x, which looked like 3x squared minus 4x plus 1 to the 5th. See if you can figure this out. Pause the video. See if you can figure this out. What would be our f of x and our g of x so that f of g of x equaled h of x? Pause it and see if you can figure it out. All right, well, again, if we start to look at this, we have parentheses raised to the 5th. So if we made f of x, x to the 5th, g of x would simply be everything inside the parentheses. All right, because if we did f of g of x, if we took g and put it into f of x, we would get h of x. All right, for decomposing the functions, you just kind of have to look and find kind of, I don't know if I want to call it a pattern, but I will. You just kind of have to look, find a pattern, and then from there, get your two different functions from that. Like here I recognize that, well, if I replace all this with an x, this is x to the 5th, and then our g of x can just be everything inside it, because when we combine those back together as f composition g of x, it looks like h of x. All right? So decomposing them takes a little bit more thinking, a little more work, but it's still not incredibly difficult. All right. So that's it for this lesson. Make sure you come tomorrow ready to work some problems. See you tomorrow.